Okay, so yeah, hi everyone. Thank you all for being here. And today we're going to be talking about sustainable polymers and kind of polymers in general, and different ways of reducing our footprint with chemistry. Again, Dr. Alex Madonic and myself, Dr. Mark Scholar, your host. And so I thought I'd start by just introducing myself and kind of my background when it comes to polymers. So I got my bachelor's degree from the University of South Carolina back in 2014 in chemistry. I actually had two majors before. I was a chemistry major. I was a journalism major, so I worked at our Daily Gamecock as a page designer. So I would take pictures from different sporting events or campus events and put them into the paper. So here's a nice image of the Williams-Brice Stadium at University of South Carolina. But once I kind of found my passion in chemistry and really particularly polymer chemistry, I started working with Dr. Brian Benzowitz. And here I'm just showing a cool image of some of my undergrad work where I took these magnetic nanoparticles and we kind of decorated them with these polymer chains, and then we could use them as this recyclable delivery system for antibiotics. And this kind of really got me engaged in the whole space of polymer chemistry. And after doing some research at South Carolina, I wanted to keep on working. So I went, got a master's degree as well as a PhD from the Polymer Science and Engineering Department at UMass Amherst, working for my advisor, Todd Emmerich. And my background and my education there was really great. I got to work on or learn about polymer chemistry, polymer physics, as well as polymer engineering. In addition to working with students and doing some of the outreach work that we're doing right now, as far as communicating science and polymers with people that are just curious that don't necessarily have a background in science. And my thesis work there was focused again on more sustainable topics to figure out ways to improve the performance of flexible solar cells. So I designed novel materials that I could put into these solar cells that we coated on flexible substrates, and then I was able to figure out ways to improve their efficiency, improve their stability. Really interesting work to do for the last, or previously I did for 5 years. And so just to kind of keep going, I've had 2 jobs since I finished my PhD. I was working at the Clorox company for a little under 2 years when I came out of grad school, working in our wipes division. So I helped design new products, either looking at different kinds of raw materials that we can get into our products that would improve their sustainability factor, as well as ways that I can improve the performance or aesthetic properties of like a wipe. So improving its smell, its feel, its cleaning performance, things that would get the consumer to want to spend more time or money using the product. But right now I've kind of shifted roles back to kind of what I did my thesis work in, working in electronics and displays. I'm a synthetic polymer scientist with a company called Inc, where I help design raw materials that could go into electrophoretic displays. So this is just a Kendall display. I feel like everybody's probably seen these. I work on all the cool molecules that go into that display, which all are really tied to polymer chemistry. And so with that little intro, I thought I'd kind of start high level to give us a good background for some of the things we're going to talk about today. So our building blocks when it comes to talking about polymers are kind of the same building blocks that we use when we're talking about any form of chemistry. We're going to be talking about atoms, and really in particular, really focusing on 4 atoms that come from the periodic table elements. We're looking at hydrogens, which tend to form a single bond in a system, oxygens that tend to form 2 bonds, nitrogens that tend to form 3, as well as carbons that tend to form 4. And so if we take all of these atoms and start to link them together into what we like to call molecules, we get these really interesting structures that have a whole slew of properties. So if we just take carbon and hydrogen and bring that together, we get things like ethylene, which is a gas that's actually contributes to the ripening of fruit. So like the way our fruit goes brown and gets a little sweeter, that all has to do with ethylene. Then if we add some oxygen into that mix and a couple other carbons and hydrogens, we can get things like glucose, which is a part of the core structure of sucrose, our like classic table sugar. And then if we want to then add even more complexity and get things like amino acids, where we've introduced some nitrogen atoms, we can also have things like sweeteners like Splenda or other artificial sweeteners that are lower in calories. And so when we're talking about polymers, we're actually just taking these molecules that we've kind of assembled by forming covalent bonds between all of these atoms, and then we're forming more covalent bonds. So in the case of a polymer, we're taking this core structure and just repeating it tens to millions of times. So we basically have these worm-like structures all composed of molecules just linked together. And so when you go from ethylene to polyethylene, you're going from a gas to something that you can blow into a film to form plastic bags that basically are the ubiquitous plastic bags that we traditionally use, but even now we're trying to be more sustainable, use plastic bags that either have less polyethylene or completely replace the polyethylene with a more sustainable polymer. That could be cellulose-based, which is just the polymer of glucose. And so this is where wood comes from, all the paper that we work with. Either some of like our clothing items actually have some cellulose in them. And then if we take a polymer of amino acids, we have a lot of things like proteins, but we also have things like, or things that are more common that you might see as far as textiles go in wool. And so all polymers are just these giant macromolecules that we've kind of strung together, making them look like worms, but they have really unique properties that allow us to have these interesting materials that we use in our everyday lives. And so you're probably seeing polymers everywhere, but some symbols that you might recognize are the recycling symbols that basically denote how difficult or easy it is to recycle a polymer. So things like PET, which are in our soda bottles or laundry detergent containers, are very easy to recycle. You can normally throw that polymer or that plastic into a recycling system and get out usable plastic that you can just remold, or you can even break it down into its constituent molecules. And then as you go down the list, all the way down to things like polystyrene, which is number 6, which is fairly hard to recycle, very energy intensive, or just not really high yielding when you want to reprocess it and form it into something new. But plastics aren't just things that we can use to hold like liquids or sodas or insulated cups. We can actually use them to do really advanced things. So a lot of photolithography that's used to design microchips that go into all of our electronic devices actually rely on polymers that form the photoresist, which allows you to kind of hit a wafer with light and basically harden certain areas that can form a pattern that creates your circuit. That all relies on polymers that can interact with light. We also have polymers that go into things like flexible cell phones that are emerging into markets as we get better and better with the chemistry, and we can design them to be more stable, as well as printing full-on aviation vehicles like this Boeing 787 Dreamliner, which is predominantly plastic with a little bit of composite material to make it stronger. And so these wings and actual like the caddy of the plane were all printed pieces made out of plastic that are just added in with a little bit of a carbon fiber to reinforce it. But this plane's a lot lighter than traditional planes that are made out of metal, and it's significantly stronger because of the polymer composite nature of it. And so beyond just that side of the technology, we actually have a lot of polymers that we tend to put into our body. So polymers that go into prosthetics, polymers that we can use for drug delivery. If you've ever had a fill-in and after they drill out whatever rod they have in your tooth and then they want to coat it with this thing that probably smells like paint and they hit your tooth with light, that's actually just a polymer solution that they coat on your tooth, and then when they hit it with light, it actually causes the reaction that solidifies it so it closes that cavity. As well as looking at things like contact lenses as well as biodegradable sutures. So polymers are really everywhere. They can do a lot of really interesting things. And I'm going to briefly stop sharing so I can do a little experiment. Great. So like I was saying, I took some Elmer's glue, that's just this polyvinyl alcohol, and then I mixed it with the borax, which is just sodium borate. And so all of the, under the polyvinyl alcohol, there are these OH groups that form the actual alcohol, as well as these OH groups that are on the sodium borate ions. And so when we mix the borax with the polyvinyl alcohol, we actually do what's called cross-linking. And so this is basically your classic slide experiment where you can take a little bit of polyvinyl alcohol and throw in some borax, and you get basically a nice solid goo. But I also added in one other component, which is erythritol. This is a common low-calorie sweetener that also has these OH groups on it. And so what actually happens in this scenario with the erythritol is that if you take some of these samples and mix it, I actually don't get a completely solid goo. I get this system that can kind of flow and still retain some of its liquid properties when I add the erythritol, because the erythritol competes with the polyvinyl alcohol with the borate, leaving us this more gooey, liquid-like gel versus this pretty much completely solid gel that I have with me now. But this is a really simple experiment. You can get borax at your local grocery store, PVOH or Elmer's glue you can get basically anywhere. And then the erythritol from Truvia is available at all of your local grocery stores. And so it's a kind of a fun experiment where you can play around with different amounts of the glue, the erythritol, or the borax to kind of control how much slimy your slime is or how solid it is. And with that, I'll kick it over to Alex to talk a little bit more about
it. Okay. Welcome, everybody. I put in the chat, and maybe I'll put it in one more time, that the American Chemical Society is inviting you to join us again next month when we'll be celebrating Earth Week or Earth Day on April 24th. We'll have an online event with more fun stuff to do, and it's free. So there's the link in the chat. Hope you can join us. That takes you to our website. And we love doing these outreach events, and we love doing them in person. If it weren't for COVID, we would be at the John Muir Historical Site in Martinez next month, out there meeting with the public and meeting with you, but we have to do it remotely this time. Okay, so that's my little plug for the ACS. Now I'm going to get rid of my virtual background, which is also promoting that event. And now you can actually see my office, and you can see that I'm set up to do a similar experiment to the one that Marcus just did. But before I do that, I just wanted to hold up an example of a recompostable plastic bag, which contains some starch molecules or sugar molecules built into the chains, so that when you throw this in a compost heap, it gets broken down. And it becomes compost and can go in your garden. Now, you should probably let your city compost this, because it might take a little while. And the same with this plastic cup, which is made out of polylactic acid. Now, lactic acid is a component of milk, in fact, or can be made from milk and from other plant sources. And these can be broken back down in compost, in a nice hot compost heap, to soil, to biological material, but they look like plastic cups. So they work for us, and then they can be composted, and they don't end up in the ocean. They don't end up in landfills. They end up in compost, which is better. Okay, the whole question of where stuff ends up is really a big one for us right now. Marcus mentioned a couple of ways that plastics might be recycled and reused. There's new processes coming up all the time. Just this morning, I was reading online that microwaves might be good at breaking down polystyrene. That, in fact, is the hardest of the common polymers, number 6, to break down. So that could be helpful. But we still have to collect the polystyrene, right? And we have to get it out of the environment and back in the manufacturing cycle so that it doesn't get thrown away. And that could reduce our energy consumption, and it could reduce the amount of pollution that we put out. Okay, I see one question in the chat. Yeah, will those bags degrade in the ocean? I believe they will eventually. They'll certainly, this will degrade in the ocean a lot faster than a polystyrene package or a polyethylene or polyester package. So yeah, they will degrade eventually. I don't know how long it takes. That's a good experiment. Someone should be doing that. Maybe we already know the answer. I just haven't found it out yet. We got to do some research.
Yeah, and there are standards. It's the ASTM. If you're really curious, it's ASTM D6400, is the standard for like compostable plastics that like we've come up as like a scientific organization. Like this is what would allows you to denote something as being compostable. So there's like the humidity conditions, the temperature, and the time for the amount of I think they look at carbon dioxide generation, mass loss, plant toxicity, and all these things to ensure that whatever is breaking down truly is like okay for the environment, but it also breaks down in like a real amount of time. That so like you can't advertise that it's compostable, but really like it'll compost in 100 years. It's like okay, this is compostable within I think 30 to 60 days is like the standard testing window.
Thanks, Marcus. That's exactly what the what our participants are asking about. Cool. Okay, so I can, and you might even add, if you have a link or any other information, put that in the Q&A for us. That would be great. Okay, so I'm going to go on and talk a little bit more about making your own polymers at home, which Marcus was just demonstrating to us, and I have some of the same materials behind me, as you can see. I'm going to share my screen for a moment, and what I'm going to show you is a couple more structures like the ones we were just looking at. Okay, here we go. Share screen. Okay, so here is glucose. This is the basic sugar that keeps us going, keeps us warm, keeps all of our cells working, keeps our brains working. But this is the basic material for plants to make polymers, to make big molecules, and they connect these up in big long chains, and what do you get? Well, you get starch. So here's starch. Now I'm going to have to reshare to make that visible to you. Okay, starch. So here's starch, which is a number of glucose molecules. It could be actually tens or even 100 connected together. And so it's a nice white powder. Back here, familiar with cornstarch. Here we go. Okay, I'll stop sharing. Here's my bag of cornstarch. We'll be using this in just a moment, right? It's a nice white powder. All right. And I'll share one more thing. If we make an even bigger polymer with sugar, we get cellulose, which is what makes plants stand up. Actually, it's part of the structure, and it's also what cotton is made out of. So I'll share this structure just to show you that there's more than one way to hook up sugar molecules. There we go. So when you put enough sugar molecules, enough glucose molecules together, and you hook them up the right way, you get this polymer, which is called cellulose, and it's the stuff that cotton is made out of. Here's my shirt. It's cotton, and it's keeping me warm. And it's nice, durable material, and yet it is ultimately biodegradable, right? There are actually bacteria and maybe even insects like termites that can digest this stuff. So, and moths actually. There are animals, and really there are bugs, and there are really bacteria that can break this down. It all comes back to bacteria. They can do anything if you give them a chance. Almost anything. They can't break down human-made polymers all the time. That's a problem. Okay. So now I will turn that sharing off so that you can actually see what I'm doing. We're gonna go in my home lab, which is actually my home office, and we're gonna make a little bit of. We're actually gonna make a super ball. So we can take slime and we can make it a little tougher and turn it into rubber. And we'll see how we get on with this. Now, if you don't know the history of super balls, I'm just going to show you that real quick. It turns out there was a chemist, a polymer chemist, someone like Marcus, who was tinkering around, and he figured out how to make this really incredible rubber material that bounced like crazy, right? And that was a cool thing, and he was trying to figure out who would be interested in manufacturing that. And what happened was he tried his own company. They weren't interested, and so then he went to Whammo, the folks who make frisbees, right? And they took him up, and they developed the process, and pretty soon they were making super balls. And for some reason, I'm not seeing this, so I got to get back to it. It's the invention that was actually on the market around 1965 and became incredibly popular. It seems that it was actually Lyndon Johnson's staff got really excited about it, thought these were really fun. Everyone had them. They were bouncing them around the White House. Hard to believe. They were making 100,000 of these or 200,000 of these every month. Norman Stingley is the inventor. He got a patent on this. Wham-O had to develop it. Let's see if I have the patent open. Yeah, here it is. I think you can see this patent. I'm still sharing the screen, right? Everybody see that? It's the picture of a ball. Here's a recipe. This was patented in 1966. It takes a couple of years to get a patent, so I'm sure they filed this earlier. But here's a description of how this stuff was invented. So yeah, if you have a clever idea and you start tinkering around, you might come up with an invention that becomes really popular. Okay, I'll stop sharing these things now. Just wanted to get that out there for you. And now we're going to go in the lab. So what's the first thing you do when you go in the lab, when you're ready to do an experiment? Well, you might think you're going to make some notes or you're going to get some equipment out. No, the first thing you do is you put on your safety goggles. Okay. Now, today we're not working with anything hazardous as far as I know. We've got starch, pretty harmless, but even starch can burn, okay? It actually can catch fire. You never know what's going to happen. So you put on your safety goggles. That's the first step. And the reason you do that is you don't know what's going to happen. You don't expect trouble, but you prepare for it just in case. Because you don't get a second chance on this, right? If something goes wrong, you want to protect your eyes. It's just like in a car. What's the first thing you do when you get in your car? You put on your seatbelt. Why do you do that? Just in case you crash. You don't need that seatbelt if you don't crash. But if you crash, you only get one chance. I walked away from an accident that would certainly have killed me. In 1980, I rolled a Volkswagen Bug. So I wear a seatbelt when I drive, and so does everyone else in my car. That's the rules, and there's a good reason for them. We're taking care of ourselves. We're keeping ourselves safe, and that's the first lesson I need to teach when I teach about laboratory work. Okay, now we're ready to do our experiment. So, in fact, I've done this already a few times, and I made notes, right? If I didn't have my notes, I wouldn't know what to do now, and if I don't make notes, I might not remember. You forget stuff, and you'll never be able to get a patent or get a publication or a degree if you don't make notes. Now, you might make them electronically nowadays, but you have to take notes. That's how you can document. That's how you can prove that you actually did something. Okay, so what we're going to do is we're going to weigh out some starch, and we're going to add glue, right, which is just like the Polymers glue that Marcus was working with. And then but we're also going to put in some borax. So that's our cross-linker. And I almost forgot, I have a little model here. So these are models of chains of molecules, polymers, small pieces of them, of course. And the red atoms here are the oxygens that are going to cross-link and hold this together. So that's exactly what Marcus was trying to show you earlier.
Alex, this is Steve. I hate to rush you, but we have about 3 minutes left.
Okay. I'm going to turn on my scale, set it for grams. I'm going to put a tablespoon of cornstarch in there. Go. And that weighs 13 grams this time. Okay. Now, to cross-link it, we need to add borax. Here it is. I can't really weigh out the amount I need. I'm just putting in an eighth of a teaspoon seems to work. So like a big pinch. And I'm going to mix that up, and I'm going to put in the glue. And I'm going to get a little cornstarch on my chair if I don't say that. Get that out of the way. Nice look. Okay, so I've got my borax. Got my borax and my starch. And now I'm going to add glue. I could measure this with a tablespoon, but I'm just going to pour carefully. Okay. let's see how that works. I just put in about 10 grams of glue, and I'm going to mix it up. And we'll see how this turns out. And then I'm probably going to have to say bye for now, but you can try this at home. And you don't have to weigh it. As I said, you can measure by volume, but it's a little less exact. Okay, so I'm going to get a kind of a stiff polymer. It's not going to be as stretchy as the one that Marcus made, but if it works out right, it will bounce. And I've had some pretty good luck with this. I should have shown you the recipe I'm using, or at least the one I started with. It's published by a wonderful writer online named Henry Helmenstein. And I'd like to put that in the chat. Maybe that'll be the thing I'll leave you with. Do I have her recipe open right now? Yes, I do. Here it is. I will put the recipe in the chat so you can try this yourself. And this was originally published by the American Chemical Society, but this author publishes all kinds of great stuff. So I hope you take a look. There it is. And let's see how my super balls come along here. It's getting a little stiffer. I might have to finish the job by hand here. Oh yeah. This gets a little messy. You should really do this in your kitchen instead of in your office. There we go. Okay, what I'm going to do is I'm going to show you how it turns out when it works right. So I tried several things, and the first one didn't work at all. Just looked like this. It was a blob. Okay, that wasn't a big success. And the second one I tried was even messier. When I got the right ratio, and especially when I put the borax in as a solid powder, it actually bounces. I don't know if you can see it, I'll bounce it over here. All right, well, that's the show. I hope you'll try this at home. If you don't mind making a little bit of a mess in your kitchen, and have fun.